All right, welcome. Let's get started for today. Your homework 2 was due last night, and your homework 3 was released and is due next week, exceptionally on Tuesday because Monday is a holiday, and so the due date is Tuesday, exceptionally next week. Your project 2 will be released very soon, and that will be due next week, Friday at 5 p.m. There will be an optional mini contest, just like there was for Project 1. That will be due on Sunday at midnight next week. The results for the Project 1 mini contest will be announced in lecture on Thursday. Starting this week, we have the exam practice sessions. What does that mean? That means that some of the section slots are still regular discussion section, doing a bit of review and warm-up exercises for the homework. But the other roughly half of discussion sections are dedicated to solving past exam questions. And this week it'll be dedicated to solving problems on search. Next week it'll be CSPs and so forth. Check Piazza for the precise schedule. You can go to both types of sections. In fact, you can go to 10 sections total if you want in a given week. The reason we have these exam practice sessions is because exam questions tend to be harder than homework questions for many reasons. One of them is simply that on exams, you're supposed to work completely on your own. You might be more time constrained. Other reasons are that you can't just try again if you get it wrong, which you can do for homework. So it's easy to underestimate when you're doing homework how hard the exam might be, and that's why we have these exam practice sessions so you can simulate for yourself where you're at in terms of mastering the materials if there were to be an exam right now. So very highly recommended. We will also record solutions, a screencast of solutions to this exam practice session handouts. So Chelsea will be the one recording those and post those towards the end of the week. If you somehow can't make it, you can still watch how one of our TAs, in this case Chelsea, solves those questions. Any questions about logistics? All right, so AI in the news. Nice article yesterday about automating Tinder with eigenfaces. Who here has heard of Tinder? Quite a few people have heard of Tinder. All right, so this will be close to your heart then. So Tinder, in case you haven't heard of it, is essentially an app where you get to see a picture of people that you might care about. You swipe left or right depending on whether you like them or not. If they also like you, you can start a conversation with them. Now, at some point it might get really exhausting to be swiping left-right. You might spend all day swiping these pictures, and now you might want to automate that. And so this article is about AI to automate your swiping. So what does it do? It has some computer vision built in. It uses the Viola-Jones face localization algorithm to find where the face is in the picture. Then it crops a box around that face. And then it runs machine learning based on your past swipes to try to predict whether you'd swipe left or right. There's an API for Tinder, so it swipes for you based on that prediction. What it uses underneath is a nearest neighbor algorithm, which is something we'll see towards the end of this semester. In a feature space that's called eigenfaces. So you might hear more about that towards the end. Then once it's done that, let's say there is a match. That means you're allowed to start a conversation with the person you matched with. It actually runs machine learning for sentiment analysis to check whether there's a positive or negative sentiment in the message you're getting from the other person. It then has a decision-making process based on the kind of sentiment that comes back. It'll send back a reply. And then, in this case, the way it's implemented, after 3 times of going back and forth, you would be notified that maybe you want to jump in now and take over from the AI to start conversing yourself. Person who builds this reports that this has been very useful to not have to swipe as much. Also, apparently found that people were intrigued that it was an app, an AI app that actually initiated the conversation. So apparently didn't hurt the way the person was evaluated in their dates. Maybe part is that they wrote it themselves, who knows? But there's a good case of AI in action to save people some time. All right, so much for AI in the news today. Let's move on to the technical topics of lecture, uncertainty and utilities. So often our outcomes are uncertain. This could be due to a roll of dice, which would be very explicit, let's say in a game. But this also could be because you don't know exactly how the world works. And so you have to model the world with stochasticity rather than deterministically. Okay, so let's say you are playing a game, just like we looked at last time. You're the maximizing player, then somebody else makes a move. Last time that was the minimizer. And then there are utilities at the terminal nodes of this game. And in this case, there is 10 and 10 on one side, and there is 9 and 100 on the other side. We looked at this last time. We said, well, if you're playing against the mastermind robot, well, you know that they're going to make the optimal move. So you want to play the minimax strategy, which computes for you what's optimal, assuming the other person plays optimally. And you'd go down this path. But if you play against this other bot that's maybe not as smart, maybe you want to go down the other path, down here, because maybe they won't make the right move. And if every now and then they don't make the right move, it might be worth going down that other path, because on average, you might do better that way. Okay? So one way to model this is that the other bot is not a minimizer, but is a player that rolls dice effectively, and we model this as a chance node. So if we model a situation as decisions being made randomly, we'll put these circles in the game tree, and those are chance nodes. Okay, so why wouldn't we know what the result of an action would be? There could be explicit randomness, such as rolling dice. There could be unpredictable opponents. For example, the ghost could do something random and you don't know exactly what they would do. Or actions can just fail. It could be that you take an action, but then you don't know what the result is going to be exactly, and it's followed by a random outcome after your action that determines where you actually end up in terms of what state you land in. Now, the values we compute, in this case, should now reflect average case outcomes rather than the worst case, because things are happening by chance, not in an adversarial way against us. So the algorithm we'll use is expect max search, which computes the average score under optimal play. The max nodes, as shown here, do still the same computation as they did in minimax, but these opponent nodes are now chance nodes. They are like the min nodes before. They're nodes you don't control, but they're modeled differently, and the computation will handle them differently. It will now average its children. So in this case, this would be here a value of 10, and this would be a value of 109 over 2. And then at the top, you'd have a value of 109 over 2, which is the highest of 10 and 109 over 2. Okay, so you compute, in general, in this case, I averaged it 1/2, 1/2. When we don't show any probabilities on these branches, we assume it's equally likely to have every outcome. But in general, there could be probabilities there that are not uniform, and you could have an alternate world in which your probabilities would have been maybe, it could be, on this side it doesn't really matter because the values are the same, but maybe on this side you could have a 1 out of 10 chance to go down here, and 9 out of 10 chance to go down here. And then the value computed here would be a weighted average, would be 1 over 10 times 9 plus 9 over 10 times 100. So in general, it's a weighted average that you use to compute the values in these expected utility nodes. Soon we'll see a different way of essentially formalizing the same thing. Soon meaning the next 4 lectures after this lecture. We'll see a related but different way of formalizing this. Today we'll look at these expected max trees. But then we'll look at something called Markov decision processes, which effectively formalize the same thing, have some advantages, some disadvantages, and we'll look at those later. Okay, just as a reminder, why we might care about this. last time we saw this demo, it was this grim world for Pac-Man, where Pac-Man is surrounded by ghosts. The game starts. The orange ghost is only one direction to move. The blue ghost can choose between two directions to get going and then keep going. If the ghosts are playing against Pac-Man, then the rational thing to do for Pac-Man is to essentially dive bomb into that orange ghost, and that is what it does when playing the minimax strategy, because that's the quickest way to die. And in this game, you lose points as the game progresses. Of course, you gain points when you eat pellets or when you win the game, but if you're going to lose anyway, might as well die as soon as possible here. Now, if the world is not such that the ghosts are guaranteed to play against you, the blue ghost is making a decision at random, then the optimal thing to do is to actually move to the left for Pac-Man. And 50% chance that would lead to still being eaten, a bad outcome, but 50% chance Pac-Man could win the game. So let's see what happens here. This is the unlucky outcome. Even though this is the Expectimax right thing to do, there is chance involved now. And even when you do the rational thing, it is possible that you don't win. It's part of what happens when things are random. You don't have a guaranteed outcome. And so the optimal action could still lead to what you don't want. Let's try this again. Okay, it's unlucky again. Let's try this again. All right, let's try this again. Again, Pac-Man playing Expectimax. Wow. Very unlucky sequence of outcomes of this chance node. Let's try it one more time. Expectimax. Oh. This morning, when I tried it, actually half the time went one way, half the time the other way, but right now the coin is coming out the same way every time, unfortunately, for Pac-Man. That's the way things can be. And if you're the kind of person who feels like they'll always be unlucky in life, you might want to play the minimax strategy rather than Expectimax. All right, so this is some motivation, and what this really is coming after is that there are two things at play here. One thing is the algorithm. There's minimax and Expectimax. And the other thing is how the world actually behaves and how we model the world affects which algorithm we might want to use. Okay, so what does the pseudocode look like for Expectimax? We'll still have a dispatch node, just like we had for minimax. If the current state is a terminal state, you return that state's utility. If the next agent to make a move is a maximizer node, you return the max value of that state. If the node you're in is a chance node, you call the expected function. What do they look like? Maximizing the value looks as it did before. X value is new and is over here. Let's look at that in more detail. So the X value initializes at 0, and then what this does here, it loops over all successors and computes a running weighted average, weighted by the probability of each successor. And then once it's seen every successor, computed that weighted average, it returns that weighted average. So here's an example. The first successor has probability 1/2, the next one 1/3, the next one 1/6. So the computation that would happen here effectively is the weighted average this way, and it would return the value of 10 up into the higher levels of the tree. Okay, let's look at this in a slightly bigger tree. So what would happen here? We have an annotated probability, so the assumption is that every outcome is equally likely. So we would work our way left to right here. This one, 3, 12, 9. So to average that, we get a value of 8 over here. Then we look the next one here, averaging that is a value of 4. Next one here, averaging that, is a value of 7. The maximizer would pick 8. Now, if it plays out as we assumed this was a maximizer followed by a chance node, then maximizer would take this action, and then once we hit this point, we don't know how it's going to play out. It could be any of those 3 outcomes. In fact, none of them has utility of 8. So even though the value at the top here is 8, the way it'll play out, the utility that the maximizer receives will never actually be 8. But on average, if this is played sufficiently often, the average will be 8. Okay, so last time we looked at minimax as a starting point, and then we started to look at some improvements. So we said, how about pruning, right? We looked at alpha beta pruning. So what happened then for the same tree is that after we had computed the value of this node, in this case that value is 8, and we saw 2 here, we're able to say we don't need to consider anything here because that 2 is worse than 8, and it's only going to get worse because that's a minimizer node at the time there, but now we have a chance node here. Can we still prune? No. Why not? Well, who knows? What if plus infinity is sitting here? Then this would be extremely good. Or if you don't allow for infinities, it could just be a really, really large value that effectively is like plus infinity for all practical purposes, and this would still be good, even though the 2 isn't that great. So we cannot prune the same way we did for minimax. In fact, without any additional assumptions, there's no way you can prune. Now, the kind of things we would like to do, and you'll see on past exam questions and maybe future exam questions, is to ask you things like, oh, what if we were to assume that it is a chance node, but values lie in the interval -5 + 5. If you know that, can you now still prune in some cases? Or if you know that the values will sum to something, can you prune? And so forth. So there's all kinds of things that, if the probabilities of each of the branches satisfy certain properties, can you prune and so forth. So we will have this kind of variance for you that essentially force you to think through exactly why could we prune in the minimax case, and what kind of tweaks and assumptions here might allow for pruning again. And the first thing we said is, well, a plus infinity could really change things up here, right? So you can imagine that something related to bounding what these values can be will allow you to do some pruning in some cases. But there are other scenarios too. So those are things to think about for yourself, kind of when might it be still possible to prune. The other thing we needed to do was to limit our depth, because games are typically many, many, many moves. The size of the search tree is exponential in the depth of the search tree, so exponential in the number of moves that you get to play until you reach the end of the game. And so often impractical to search all the way till the end and to actually see what the terminal utility values are. And so we said we need to cut that short. We'll have an evaluation function that tells us approximately how good it would be to reach that state. It's not going to be exact typically because we don't know how good it is. We'd need to do that full search in that subtree to know how good it really is. But we'll have some evaluation function that's a reasonable approximation and use that value to limit the depth of the search. Okay, so we can do that in expect to max too, no reason not to. Okay, so now what we've encountered is probability kind of for the first time in this course, and we'll see a lot more probability in the next 10 lectures. So let's do a quick reminder of some of the definitions there. So a key concept in probability theory is that of a random variable. A random variable represents an event whose outcome is unknown. The probability distribution associated with that random variable will assign a set of weights for each possible outcome. There are some laws about those weights. They all have to be positive. Can be 0, but not less than 0. Probabilities over all possible outcomes have to sum to 1. Okay, here's an example. We could have a random variable indicating whether there is traffic or not. we then, as engineers modeling the world, decide that there are 3 possible values for this random variable: no traffic, light traffic, heavy traffic. We can then somehow come up with weights for this. We don't know yet how to do that, but let's say we had some weights. We say probability of no traffic is 0.25, light traffic 0.5, and heavy traffic 0.25. These sum to 1, they're all non-negative, so it satisfies the requirements for a probability distribution. One thing I want to foreshadow here is that often what will be important is that these probabilities can change. Right? For example, it could be if now somebody tells you, we're thinking about traffic at a certain time of the day, let's say 8 a.m., that distribution will change because now I say, well, a priori, I thought it was 0.25, 0.5, 0.25, but now that I know it's 8 a.m., probability of heavy traffic becomes much higher and the distribution changes. Okay, so the key concept we need today is that of expectations. And the expected value of a function of a random variable is the average weighted by the probability distribution over outcomes. Let's look at an example. How long to get to the airport? We have a distribution over possibilities for the type of traffic there is. Then the thing we're interested in is how long it will take to get to the airport. So for each type of traffic, we have a duration associated with it, 20 minutes, 30 minutes, and 60 minutes. And the expected value of how long it takes to get to the airport is now the weighted average of these values, in this case, 35 minutes. Okay. Hopefully you've seen this before, and this is fairly straightforward. If you haven't seen this before, we'll see a lot more of this, so make sure you become really familiar with these types of computations. Now, the question, of course, becomes, now that we know how to compute expected values, where do these probabilities come from, right? In Expectimax search, we assume we have some probabilistic model that tells us for each of these chance nodes how the opponent or environment will behave in any state. And this model could be simply a uniform distribution, roll of a die, for example, flip of a coin. It could be something more sophisticated, where you simulate something, how things might play out and so forth. There's some complicated computation that tells you what the probabilities are. We'll see some of those about 5-6 lectures from now. Could be a chance node that's out of our control, or it could be something that is controlled. So it could be out of our control because it's controlled by an opponent, or it could be out of our control because it's controlled by nature, so to say, the environment. So there could be different reasons that this is a chance node. In some cases, it might actually not be really chance at all. We might be playing an opponent who has a deterministic strategy, will always do the same thing in a given situation. We just don't know what it is they would do. And the best way we're able to model it is by assuming randomness. Could say that this opponent likely takes adversarial actions, but not always, and so forth. Where do the probabilities come from? For now, we'll just assume they're fed to us by a probability fairy who tells us this is what's the probability for each possible outcome. But the second third of 188 is primarily about computing these types of probabilities when you have distributions with lots and lots and lots of random variables, and where the naive way of computing these probabilities would be very expensive. Okay, but for now, we'll assume that these probabilities are provided to us, and we can work with them as provided. All right, so let's do a little quiz on this. Let's say you know that your opponent is actually running a depth 2 minimax, using the result of this 80% of the time and moving randomly otherwise. Question here is, what tree search should you use? What does your game tree look like to model this particular game situation? Any thoughts? Over here.
Expected max for you're using the max thing normally, but then for the expected one, on those nodes you actually run a depth 2 minimax yourself and then assign that, like whatever node that tells you to pick, do a probability of 0.8 to it, and then like also add in like randomly like equally distributed for the rest of the probabilities.
That's a perfect answer. I'm going to repeat it just so everybody can hear it through my mic. But so the answer here is what's actually on the slides. So you can run Expect-to-Max, which would look like this, because your opponent is modeled with a chance node. You don't know what they're going to do. There's something stochastic there. But then the way you compute the distribution over possible actions is by inside each chance node, you have to run a little minimax search for your opponent, modeling the thinking of your opponent. The opponent thinks that they might play like a minimizer, do the depth 2 search for a minimizer in that situation. Assuming you play as a maximizer, you compute the outcome from that computation, then give that a 80% chance in your chance node, and you give 20% chance to random other actions. Okay, so what happens here is that effectively you have a search inside a search, right? Now this could get more complicated, right? Because you could imagine that now the minimizer is thinking that you play according to a certain way, and that you in turn are thinking that they play according to a certain way, and this could recurse for quite a while. You have to think about how often do they think about what the other person will do, what they then will do, what the other person will think they will do, and so forth. So there's a question there, where do you stop? In this case, it's just stopped here because the assumption was that the other player is just doing this one computation without thinking about what you are thinking, that what they would be thinking, and so forth. But in principle, you could have a whole chain. This can get very complicated in terms of getting searches inside searches. There's a very special case, actually, where these searches inside searches simplify drastically, and that is in the case of minimax. So what we've seen so far for minimax, we've seen one tree in which we compute. If you, instead of having that one tree, did a search within 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 a search till you hit the bottom of the game, where every player thinks the other person will play minimax, these searches inside searches will reduce to your original minimax tree. But for pretty much any other scenario, if you're starting to model how the other player will play, you get searches inside searches and so forth. Okay, so modeling assumptions are really important. We now have algorithms, but how do we model what's happening? What are the consequences of how we model things and then which algorithm we use? So there are dangers to being optimistic. Assuming things play out by chance when the world is actually acting against you can be a bad thing. And here's a cartoon for that. Let's say you're encountering this really scary situation, but you say, well, I'm kind of a happy robot. I'm going to take my chances. Things might not turn out that well for you. But being pessimistic can be bad too. Let's say you're this little robot, and when you encounter this cute little bunny, you think it's Bunny-Clyde, the vampire bunny. You're going to be scared and act worst case scenario in your mind and never have the kind of optimistic outcomes that you might get more typically if the world is really nicer to you. So let's look at some examples in the case of Pac-Man and the ghosts. So we have a grid here. And in the grid here, we have the algorithm for Pac-Man over here. Pac-Man could run minimax or could run expect-to-max. The ghost could be an adversarial ghost or it could be a random ghost. Bless you. Now, what we've looked at so far is the scenarios where we say, well, if we have an adversarial ghost, we want to run minimax. If we have a random ghost, we want to run expect the max. So these are the natural scenarios, but we could also look at what happens if we run a mismatched algorithm with what the world is like. You might not do this intentionally, but if you're not really sure what the world is like, you might want to be aware of, well, what would happen if my assumptions are wrong? How would things play out? So let's look at some demos here. We'll start with the things we're familiar with, and then we'll start looking at the mismatched cases. So the first one is a scenario where the ghost is acting randomly. Ghost is acting randomly, and Pac-Man matches that with its algorithm and plays out expect the max. So actually, let's start this. Ooh, it played it on my screen on this side over here. Let me see if we can change that. Ooh, it's playing too quickly. Let's try that again. Give it some space here. Keeps playing it on my screen. All right. Let's give it even more space, maybe. Oh, Pac-Man. All right. This is not straightforward. Let's do it this way. Keep showing it on my screen. Okay, this is let's look at the video version because it's always popping it up on my screen instead of on the projected screen. So here is the first scenario. We have a random ghost, Pac-Man playing expect the max. What's happening? Optimistic assumption about the ghost. The ghost does move randomly, and so this plays out pretty well. Next one here. The ghost is adversarial. Pac-Man plays minimax. Let's see what happens here. There's a minimax depth 4. So it's kind of cautious about staying away from the ghost and then makes its way to the dot. It's a lower score than expect the max because it took longer to get there. But if the ghost is really working against it, it might be the right thing to do. Now let's take a look at what happens when assumptions are mismatched between the algorithm and the world. So in this case, it's expect the max Pac-Man, but an adversarial ghost. So Pac-Man is optimistic, the ghost is adversarial. This case happens to work out. So even though the ghost was trying to track down Pac-Man, Pac-Man was optimistic and got away with it. At times this will not work out. It'll be too optimistic and the ghost will actually track it down. Then here's the case where the ghost plays random, but Pac-Man is playing minimax. Yay. So let's take a look at what happens. The minimax scenario will play out the same way every time, of course, but that when the ghost is playing deterministically, it'll play out the same way, but if the ghost is playing with some randomness, the outcomes vary, so we need to do multiple runs to see on average how things play out when the ghost plays random. So Expectimax playing against a random ghost wins 5 out of 5 because it anticipates that randomness pretty well, and average score is 503. Minimax against an adversarial ghost is a worst case world to be in, right? If the ghost is playing Minimax, you're never going to do as well because it's just not as good a situation to land in. Playing Minimax, we still get an average score of 483 and wins 5 out of 5. Now when we have a adversarial ghost, but Expectimax Pac-Man, it wins only 1 out of 5, and the average score is minus 303. So we saw one of those lucky wins. And then the random ghost playing against the Minimax Pac-Man, which we saw last, where Pac-Man's very conservative, stays away from the ghost, and finally when it's really, really sure it can make it to the pallet without getting caught, it goes there, wins 5 out of 5, but the score is lower than if it were to play Expectimax, or the average utility score is lower because it's playing more conservatively, even though the ghost is actually not that adversarial. The details are down here. So Pac-Man, in this case, used a depth for search, which could be an Expectimax or a Minimax search, and the ghost used a depth to search either. In the case it's playing adversarially, it's just moving randomly when it's playing in the random ghost scenarios. Okay, so that's assumptions versus algorithm you might use. Now let's take a look at other game types. So far we've looked at adversaries that are modeled as playing against us or playing by chance. Now let's look at something else. Here's an example, Backgammon. One of the first games actually people start looking at to build AIs for. What's going on there? Before you get to make your move, you actually roll dice. So as a maximizer, when it's your turn, you don't get a choice of action straight up. You roll dice, which has a... So actually, sorry, it's not exactly... So let me clear the slide here. As a maximizer, you roll dice, so you would in some sense have multiple possible outcomes. These would be chance nodes. After those, so now I guess in this case what we have in really is the minimizer we're looking at. The minimizer is playing. After the maximizer made a move, it's the minimizer's turn in some sense, but first dice are being rolled. After the roll of dice, the minimizer has a set of options available and takes an action. And so even though really the minimizer might be the one here rolling the dice and then taking an action, the way this is modeled in the game tree is that there's first chance nodes, which are the dice, and then there's the minimizer nodes where effectively you get to choose your actions. So these rolls of dice are modeled as chance nodes, random outcomes, and you could have trees where you have maximizer nodes, chance nodes, minimizer nodes, interleaved in any possible way, just modeling however way you play the game that you're playing. So a little bit about Backgammon. It was actually the first game where there was an AI world champion. Okay? Let's take a look at what goes into building an AI for Backgammon. So first you roll dice, 2 dice, so there's 21 possible rolls here. Then you have roughly 20 legal moves for a given roll of dice. So your branching factor is some 21 times 20 every time somebody plays. Then if you do a depth to search, you need to count, see how often this happens. And you have essentially this many things, roughly a billion things to look at with your evaluation function for just a depth to search. As your depth increases, this will just get larger and larger and larger. Now the nice thing about the randomness is that in some sense looking deeper and deeper becomes less and less important, because it's not that the game might play out guaranteed if you play against the optimal player in some particular way. There's many possible ways it could play out, and so your evaluation function is approximate, your averaging outcomes is often it's not as bad to have an approximation as it would be if you had an actual purely adversarial game with no chance nodes. So limiting depth is less damaging here, but the pruning is trickier because of the chance nodes. What they used to build that first AI world champion in backgammon was a depth 2 search with a very good evaluation function. That evaluation function was not set by somebody by just saying, oh, here's a good evaluation function. They used reinforcement learning, something we'll cover in the next 4 lectures, to have the system play itself to learn a good evaluation function from self-play. And then once it had learned that good evaluation function from self-play, it would use it to play against human players and become world champion. Okay, so here's another generalization of games. You could have more than 2 players. So in this scenario here, there are 3 players. There's a red player, a blue player, and a green player. At the terminal nodes now, we have 3 utility values. A red one, a blue one, and a green one. The red value over here is the utility. If the game would end up over there, red player would have a utility of 1. Blue player would have a utility of 6. Green player would have a utility of 6. That's the meaning of these terminal utility nodes. How does this play out? Well, the green nodes are where the green player makes a decision, blue where the blue player makes a decision, red where the red player makes a decision. So we can again propagate from the bottom of the tree. We have the green player here. Looking at these 2 options, the green player will say, well, a 6 is better than a 2. That's all they need to look at, the green values. So they will prefer this outcome over here. That's how the game would play out if it reached that point. Now, over here, how the game would play out is 2 is better than 1, so green would go this way if ever the game reached that spot. Then the blue player here, if ever the game reached that spot, knows what the green player would do and can now say, well, the green player would in one case end up here, the other case over here. A 6 for blue is better than a 1 for blue, so blue would play this way. The other side, we can do the similar reasoning. 7 is better than 2 for green, so if the game ended up over here, green would go this way. If the game were to end up over here, green would play this move and end up over here. Blue now knows what green would do after its action on that side of the tree. And so blue says, well, 2 is better for me than 7. So I should go this way because then green will go this way and that'll end up in 2. If I play the other move, I'd end up with a 1. Now, red can start comparing. So red knows what blue and green would do in any possible situation they might encounter, and knows that if the red were to go down this way, the game would play out to end up over here. If red were to go down the other way, the game would end up over here. The right side has a utility of 5 for red, the left side 1. 5 is better, so red will play this move over here, and the game will play out this way and end up over here. Question?
So, does green just want to maximize its own utility, or does it also want to minimize the utilities of red and blue?
So that's a good question. And what we've seen so far, we always had only one utility at the bottom, and the maximizer was maximizing this, the minimizer was minimizing this. In this kind of game, the way we define it is that you don't care about the utilities of the other players. You just care about your own utility. That's how utility is defined. Now, if, let's say, the green player were really good buddies with the blue player and would love for the blue player to have a good outcome, the way that would be encoded would be that the utilities at the bottom here would be such that when blue has a low value, green would have a low value too, because that's how their utility is defined. So the utilities are coming in and are supposed to already encode what you care about in terms of what the outcome of the game is going to be, and then you work with those utilities. Now, with these utilities here, still interesting patterns emerge, right? Because if the game were to land over here, you see blue and green are collaborating because 6 and 6 is best for blue and green, and that's where the game would end up if we were to land over here. Now, that doesn't mean everywhere in this tree blue and green would collaborate in that sense. It really depends on utilities that are sitting in a subtree, what kind of pattern that emerges. It could be adversarial, it could be collaborative, it could be sometimes collaborative, sometimes adversarial, and so forth. So you can get any kind of dynamic here depending on how utilities are defined at the very bottom. Okay, how does this relate exactly to what we've seen so far? We now see a multi-agent game tree. Let's say we were interested in saying, well, I have a 2-agent game tree, right? Special case of multi-agent game tree would be a 2-agent game tree. We've already seen those in some sense, but they had only one value at the bottom. So what's different here? If you were to turn a minimax tree into one of those multi-agent game trees, now you'd have 2 values at each leaf. The maximizer value would be what we've already been using. The minimizer value would be negative of that. And then you get the equivalent as what we had before. Solving that kind of game, the way we just defined here, would give the same outcome as what we've done so far for minimax. It's just that in minimax, we have essentially multi-agent game trees where it happens to be that the minimizer always has the negative utility of the maximizer. And so we're saying, well, we might as well just keep track of one number instead of 2 numbers because we know the other number is the negative. But keep in mind that it's just a very special case of what we're seeing over here. Okay, let's take a short break here, and after the break, let's look at where these utilities might come from. All right, let's restart. Any questions about the first half of lecture? Okay, so far, utilities have really been at the core of everything we've done, right? Very first lecture we said the way we define a rational agent is one that maximizes expected utility. We've put those utilities at the bottom of our game trees. We've assumed that they're there, that they exist. In the remainder of this lecture, we're going to look at where do they come from and why is it even meaningful to think that there would be utilities? Okay, so why should we average utilities and not minimax? Well, we have some intuition there that we don't want to be too scared when it's not necessary, but why is averaging really the right thing necessarily in a stochastic world? Okay, so the principle of maximum expected utility says that a rational agent should choose the action that maximizes its expected utility given its knowledge. Right. So this stochasticity is relative to the agent's knowledge. It could be that there are actually random events that are really random happening. It could be that the agent has a belief about how the world works. That's a stochastic belief about how things would turn out. It could be a stochastic belief about how the opponents play and so forth. But it's maximizing expected utility will say, assume your agent has some belief that hopefully is as accurate as possible, then to be rational, that agent should maximize expected utility with respect to that belief. Okay? Well, where do these utilities come from? How do we know they even exist? How do we know that averaging actually makes sense once we have them? And what if our behavior or our preferences cannot be described by utilities? Okay, let's start with what utilities to use. So here we have 2 game trees. Let's look at the left one first. If we play minimax in this game tree, what will happen? Well, we'll have a worst outcome here of 0, worst outcome here of 20, and we'll go this way. If we play minimax on the right, what will happen? Well, all we did is square the bottom values. Squaring the bottom values, if they're all already positive, doesn't change their ordering. So the branches that will be chosen in a given situation will still be the same because the ordering among outcomes is the same. And so you don't even have to compute values. You know that the game originally would play out this way, and you know now will play out this way because all you did is square the values in monotonic transformation that doesn't affect how the game will be played. So actually for minimax, how we choose those values that we put at the terminal nodes isn't super sensitive, isn't all that critical in some sense, because when we transform them, we might still get the same outcome. Now let's take a look at what happens when we were to play Expect-a-max. So when we do Expect-a-max, we assume this is a chance node, this is a chance node, this is a chance node, this is a chance node. We'd get 20 here, 25 here, play out this way. Second game tree, we get 800 here, we get, let's see, 650 over here, and now we play it out that way. So after a monotonic transformation of the leaf nodes utilities, we actually would play the game differently. So one thing that we can realize here is that the exact values we choose at the leaf nodes for our utilities becomes quite important once we use Expect-a-max. Okay, so the magnitudes now need to be meaningful. We can't just say of all possible game outcomes, give us an ordering. You actually need to give numbers for these outcomes. All right, so utilities are going to be functions from outcomes, which are states the world lands in at the end of the game, to real numbers that describe an agent's preferences. Well, where did it come from? In a game, it might be as simple as a +1 or a -1, depending on whether you win or lose. They are the summary of the agent's goals. By specifying those utilities, you define the agent goals. There's a theorem, and we'll look at that soon enough, that any rational preferences can be summarized as a utility function. So if your preferences are rational, there exists a utility function that summarizes them. Okay, well, in this class, the way we do things, we hardwire the utilities and let behavior emerge through search in a tree that uses those utilities. Why don't we just let the agent pick their utilities? Wouldn't that be like a cooler way to do AI? Because now you don't even have to specify the utilities anymore. The agent will also take care of that. Well, that's kind of problematic, because if the agent picks the utilities, essentially you have no control over what they're going to be doing, right? If their utilities are misaligned with yours, then the outcome of running their search will be misaligned with what you desire, and now your agent will essentially do whatever they want to do, and it's not what you want them to do typically. So you might say, well, how about something else we can do instead of specifying utilities, which is we specify behaviors. Well, we saw that in lecture 1. We talked about this. It's called a reflex agent. A reflex agent is an agent where you just code, in some sense, reflexes based on what the situation is. You write a piece of code that says, in these situations, do that, and so forth. For very simple situations, that might work. But now it becomes very difficult to get an agent that behaves really well. So often it's easier to specify utilities than it is to directly specify a behavior. Now, I've referenced to these, and you've seen probably a lot of these articles in the news where they say, oh, we need to be careful. What if AI goes rogue and kind of, does all kinds of bad things? Technically, what that means for AI to go rogue, it could mean two things, really. It could be that somehow the AI starts picking its own utilities, optimizing for those, and they might not be aligned with ours. So that'd be one way for AI to go rogue that we might want to avoid. Another way AI could go rogue is that essentially we just picked the wrong utilities, and it's optimizing them really well. It's doing what we asked the AI to do. It's doing the rational thing, but we gave it some utilities that just happen to not be aligned with what we actually want. We just picked wrong, and it's really good at doing that thing that we asked it to optimize for. So these utilities are actually critical in terms of what your AI will do, and in the long term, sometimes as AI becomes more and more powerful, it becomes more and more important to be really clever about choosing the right utilities for your AI. Okay, So the key thing we care about here is how to deal with the utilities when there are uncertain outcomes, because that's when it gets tricky. If outcomes are all deterministic, it's not that hard to figure things out. So let's look at an example. Let's say you're getting ice cream. You could get a single scoop or a double scoop. Get your single scoop, pretty happy. Get your double scoop, well, you might just drop it because it's more difficult to handle. Or you might be super happy if you saved it. Okay. So while it's pretty easy to order these outcomes, to say this is the most preferred one, this one is second, and this one is third, to decide what to do in this kind of situation, you need to know more than just the ordering. Because just knowing the ordering doesn't tell you whether to go left or right. You need to know, depending on the probabilities on this oops or phew branch, whether you'd prefer to go to that stochastic outcome branch than, well, the deterministic one with one scoop. Okay, so let's look at preferences. So a basic concept here is prizes. Prizes are values associated with specific outcomes. So these are numbers. Like you could have a prize of A, which would be a number for having one scoop, a prize of B for having 0 scoops because they're on the ground, and a prize of C, which is to have the two scoops left to you. Lotteries are situations with uncertain prizes. So these, the situations I'm circling here are all prizes. This could be A, it's willing to register, A, B, C. But then this here would be a lottery over outcomes. And there would be probabilities associated with it, in this case, P and 1 minus P. Here's some new notation. If we prefer prize A over prize B, that's how we denote it. If we're indifferent between them, we have the little squiggle between them. Okay? So here is how it look in some kind of game tree. We could have just an outcome, some kind of prize, or a lottery between prizes. The way to think of this is not as playing the state lottery or anything like that. Lottery here means something very specific. It means that you are in a situation, or are going to be in this lottery situation, where 2 outcomes are possible. One outcome is A, the other one is B, and there are probabilities associated with them. Okay, so let's take a look at rationality. What does it mean to be rational? Well, we're talking about preferences here. We're trying to be rational about what we prefer over something else. A first action we might put forward and say an agent can only be rational if, at the very least, their preferences satisfy the axiom of transitivity. Saying A, if A is preferred over B and B is preferred over C, then if you ask that agent, do you prefer A over C, they must say, yes, I also prefer A over C. If they wouldn't prefer A over C, that would be an agent with irrational preferences. Okay, why is that a reasonable assumption? Let's say we encountered an agent with irrational preferences. We can play a little game with that agent. Okay, it depends on the exact preferences, but roughly the game will play out like this. If they prefer B over C, and let's assume we have a hold of A, B, and C stash, so to say. We only need one of each. If they prefer B over C, then the agent would be willing to pay, let's say, 1 cent in exchange for giving up C and getting B, because it prefers B. B is better than C, so it'll exchange C and 1 cent to you, and you'll give it B. Okay, after you're done with that transaction, you go back to that agent and you say, well, I heard you prefer A over B. I just gave you B. How about you give me B back and add 1 cent to it, and I'll give you A. Agent will say, well, yeah, I prefer A over B. That's good to me, and the difference is roughly 1 cent, let's say. So that's a good deal for that agent, and they'll have now A. Then you go back to that agent and you say, well, I heard you also prefer C over A. Let's do another transaction here. And I just gave you A. Well, why don't you pass me A back, add 1 cent to it because you prefer C, and I'll give you C in exchange for A and 1 cent from you. Now you've gone full circle. What's happened is the agent is back to having C, which they had at the very beginning of this circle. While traversing this circle, they've lost 3 cents, and you can actually play this game again with this agent. You can keep going around and around and around if their preferences are such that they prefer B over C, A over B, C over A, and the difference is, let's say, at least a cent in terms of how much they preferred one over the other. Okay, so I think most of us will agree that you want your preferences to be transitive. There are a couple of other actions that we'll posit. Orderability. A has to be preferable over B, or B has to be preferable over A, or you have to be indifferent between them. One of those three has to be true. Transitivity is the one we just covered. Continuity, that's kind of the most subtle one in many ways. If you prefer outcome A over outcome B over outcome C, then there must be a probability P, a number between 0 and 1, such that you are indifferent between that middle one B and a lottery over A and C for some value of P. Okay? Substitutability, if you're indifferent between A and B, then if you have a choice between 2 lotteries that have the same probabilities and are always considering C either versus A or versus B, then you should be indifferent between those lotteries too, because the only difference between the lotteries is that A is here and B is here, and you're indifferent between A and B. Monotonicity says that if you prefer A over B, then lotteries where the probability of A is higher than so if you have 2 lotteries and P is higher than Q, meaning in the first lottery, the probability of having A is higher than it is in the second lottery, you must also prefer the first lottery over the second lottery. So these are 5 assumptions. These are axioms. We're not proving those. We're saying we think that to have an agent with rational preferences, that agent's preferences need to satisfy these relations. Okay, so now there's a theorem. It says that if these 5 axioms are true, you're willing to work with those, this implies that the behavior is describable as maximization of expected utility. Okay? So if you're willing to agree with these axioms, that means everything we've been doing about maximizing expected utility is indeed the right thing to do. Okay? All right, so let's assume our agent is stamped with this rational preferences kind of certification. Let's make this a little more precise. It turns out that the theorem says that if preferences satisfy those 5 axioms, there exists a function u, which we call a utility function, that if and only if A is preferred over B, the utility assigned to A will be higher than or equal to the utility assigned to B. That's for prizes. And for lotteries, we have that the utility of a lottery will be equal to the average, the weighted average of the utility of its outcomes. Okay, we're not going to prove this theorem. It's actually a pretty old theorem, but it's essentially the theorem that justifies that we work with utility functions and that we say maximizing expected utility is the rational thing to do, because if you assume these axioms are rational in terms of how your preferences should be, this implies that there exists such a utility function. Okay? Okay, so we now know that it's rational to do this. As we covered in the very first lecture, it doesn't mean every rational agent explicitly maximizes expected utility. They might do something else that you hard-coded that happens to correspond to the same actions. But a good way to design rational agents is by having them maximize expected utility. Question? Okay, so what this notation is saying here, it's saying that, So just the square bracket part is saying that this is a lottery over n possible outcomes. The possible outcomes are S1, S2 through Sn. And the probabilities of each of those outcomes are P1, P2 through Pn. So the square brackets makes that into a lottery over those outcomes. And then the utility put around it is something that computes a real number for what's inside the brackets, in this case for a lottery. But in the first line, it computes a utility for just a single outcome that's deterministic. So the utility function can be applied either to prizes directly or to lotteries. It applies in both cases. Okay, so we now know that having utilities can be the right thing to do. But how do we get those utilities? For example, if we really want our agent to optimize what we care about, we need to know what we care about. How do we get human utilities? Like, what would be the right decision if you can spin this wheel or pay some amount of money to pass on having to spin that wheel and potentially having that terrible outcome of dying? Okay, so one thing you can do is you can normalize utilities. So it turns out that if you rescale utilities by a constant positive number, everything you do will stay the same because expectations, the expected value of a rescaled version will be the rescaled version of the expected value, and so the rescaling doesn't affect the ultimate outcome. Okay, so we can rescale everything between 0 and 1. The currency we could use is a micromorph. It's a 1/1,000,000th chance of death. This is very useful for situations where you care about reducing risks of something going terribly wrong. You want to say, well, how much more money should we invest to avoid the chance of to reduce the chance of somebody dying from this? Okay. There's another measure people often use to measure utility, which is quality adjusted life years. So this is useful for medical purposes. If you kind of get sometimes to make a decision between living long with a very poor quality of life or living shorter with a higher quality of life, that's the currency you might want to use there. Keep in mind the behavior is invariant to rescaling and adding a constant, assuming a positive rescaling. As long as the prizes are all deterministic, there's no lotteries, it's very easy. We just need to order the outcomes. But once we have lotteries, we need to average the numbers that we get. And that averaging, well, that result depends on the numbers we assign, and so we need to get some numbers here. So we need a map from states of the world to real numbers. What could those numbers be? Well, here's what you could do. Essentially, it's this situation that you will play with people, but you'll say, what would you prefer, spinning this wheel or paying a certain amount of money, right? So you pick a best possible prize, and that has some utility U plus, which is the maximum utility you can possibly get. A worst possible catastrophe has some probability 1 minus P. You take a lottery between those two, and you start asking people, would you be willing to play the lottery between those two, or would you rather pay $30? Right? So specifically, this could be your lottery situation. And if you now want to measure how much is $30 worth to you, you can measure it in terms of micromorts. And so, for example, if $30 is the equivalent of a micromorph to you, which is a 1,000,000th chance of dying, right? Then now you can put that all on the same scale. And for any possible thing you encounter, you could try to compute what probabilities 1 minus P and P have to live on this decision tree for you to be ambivalent between playing the game shown there and the other thing we're comparing it with, and that value P will then measure your utility for the alternative to playing that game. Okay, so P will be between 0 and 1, and you could put anything there. You could say, well, how about being guaranteed an A plus in 188? Now, well, have things just go whatever way they will be going. Well, would you rather have that guarantee, or would you rather play this game over here? you'd have some probability there in terms of being willing to play the game relative to get the guarantee, and then that probability would correspond to your utility for getting this other outcome. Now, one thing you might wonder is, how about money? Money is a common currency. You can buy a lot of things with money. It's kind of meant to be this common thing that you can exchange for pretty much anything. At least that's the idea, but it's not the same as utilities. There's an important distinction here. So let's take a look at, let's assume you're given a lottery between monetary outcomes, right? You could add X dollars or Y dollars, probability P or 1 minus P. The expected monetary value, so the expected amount of money you're going to get, would be this quantity over here. But the utility of being faced with that lottery is not the utility of this thing over here. The utility of being faced with that lottery is this thing over here. It's an average, a weighted average of the utility of the first outcome and the utility of the second outcome. And actually, often, the utility of the lottery is smaller than the utility of the expected monetary value. What do I mean with that? It means that most people are risk averse. They'd rather have some lower guaranteed amount of money than a lottery where you have uncertainty between two values with a higher average between those values. For example, a lot of people will have a utility curve that looks like this as a function of money, where having more money, once you have more money, getting a little more beyond that is less valuable than when you have very little money, where getting a $30 extra, so to say, would be worth more than once you already have $1 billion, right? So here is how insurance companies in some sense take advantage of that, but also help you with that. Let's say you're faced with a lottery where you can either win 1,000 or win nothing. Each 50-50 chance. Okay. The expected monetary value is 500. That's on average what you would get. What is the certainty equivalent value? Meaning, what is the value of money you'd rather take guaranteed to forego this lottery? For a lot of people, that would be around $400. They'd rather get, or equivalently get $400 in cash to playing this lottery between 1,000 and 0, where they have 50-50 chance of winning. Okay. The difference between the 500 that you would get on average and the 400 that you'd rather be guaranteed to get, that's the insurance premium you're willing to pay. That's essentially what insurance companies do. Insurance companies essentially say, in life, you're constantly faced with lotteries with uncertain outcomes. If you pay us a premium, we'll guarantee you the outcome. The outcome will always be the same. Let's say, whether you get in an accident or not, your car will still be working the next day or a few days later and so forth. And so to get rid of that uncertainty, you're willing to pay a premium. You're better off because you now got rid of your uncertainty. And the insurance company, well, why are they okay with this? They get this deal with so many people that the law of large numbers will kick in for them. And they essentially are guaranteed pretty much to get that monetary gain because there's so many things that average out. Okay, so this is a win-win. Now that we know how this all works and we know how money might relate to utilities, but it's not the same thing, let's do a little thing about, are humans really rational? So here's an example from psychology research. Let's say you're faced with the choice between two lotteries. The first one is 80% chance of getting $4,000, 20% chance of getting nothing. The second one, you're guaranteed $3,000. Who prefers A? Who prefers B? So most people prefer B. I don't have that money to give you, but just a thought experiment. Now, let's do another thought experiment. You get to choose between C, where you have a 20% chance of getting $4,000, 80% chance of getting nothing, or D, where you have a 25% chance of getting $3,000 and 75% chance of getting nothing. Between C and D, who prefers C? So a lot of people like C. Who prefers D? Some people prefer D, not as many. statistically speaking, most people, as we saw in this room, will prefer B over A and C over D. Now, let's investigate whether these preferences are actually rational. Okay? If the utility of $0 is 0, we can always rescale and shift utilities. Then, preferring B over A means that we say that the utility of 3K is higher than 0.8 times the utility of 4K. If we prefer C over D, we're saying that 0.8 times the utility of 4K, well, this is 0.2, this is 0.25. We multiplied this with 4. All right, this started as 0.2 and 0.25, but we multiplied both sides with 4, and now we have 0.8. Utility of 4K is higher than the utility of 3K. Okay, now let's compare what we have here. The first line says one thing, and the second line says the exact opposite. So that means our utilities as expressed are irrational because, I mean, that's exactly what it means to be irrational. You make these inconsistent decisions. So what's going on here? Well, this is kind of stuff people study in psychology, right? And trying to understand how humans make decisions, and are humans maybe not rational? Or, so that would be one explanation. Another explanation, which might be closer to the truth, is that maybe people who have these preferences are rational, but we're ignoring some factors here. When we look at these lotteries, we're just looking at the numbers. But there's also a psychological effect. There's the effect that if you get you choose the first lottery and you get the 0 outcome, which will happen sometimes with possibility, you would feel so stupid because you could have picked that other lottery where you would have won more money. And so really, what's sitting here is not just 0 as the prize, but it's 0 as well as feeling stupid. And so once we include that in our utility calculation, this whole thing actually shakes out properly and is compatible with our preferences. All right, next time we'll look at MDPs.